Okay, hi everyone. Welcome to another episode of Robo Papers. So today, super glad to have Emil Barr joining us, talking about his paper, Navigation World Models. Happy to have you on the show, Emma.
Thank you so much for having me. I appreciate the invitation.
Yeah, of course. Thanks for making the time. Maybe as a start, if you can share a little bit about yourself, how do you get into like this kind of research?
Yeah, my name is Amir. I have a disclaimer. I'm not a roboticist, so thank you for inviting me to your podcast. I mostly have been doing work on computer vision and deep learning, and right now I recently graduated from my PhD, where I was a student at Tel Aviv University, and I also affiliated with UC Berkeley, and recently joined the FAIR as a postdoc. Yeah, that's just a bit about me.
Yeah, awesome. Yeah, okay, cool. Then I guess we can dive straight to the paper. Yeah, could you share a screen?
Yeah, sure. So let me share the screen.
Okay, perfect. Yeah, we can share a screen.
Cool. Yeah, so I don't know, maybe we should, before we just jump into the paper, do we want to talk about what is a word models? What is a word model? What is the origin of word models? Why do we need, word model, which is a hot topic right now, hot research topic right now.
For sure.
Yeah, I think it's a good idea. Yeah.
But
why do we need world models? Yeah.
Why do we need world? Yeah. But I think, so what is a word model? I mean, first of all, the term is kind of like a new branding in some sense of a term which has been quite old, right? So a word model, what we consider a word model right now is a model that takes in some state. Usually right now the state is could be based on the input sensory, like an image, and then it takes another action, like the image and some associated action. And what it does, it outputs the next states, which is, let's say, the next image corresponding to this environment. So in some sense, it simulates the world. And this idea of having this kind of models that can simulate the dynamics of the world is not such a new idea. It's something that has been with us, I think at least from the 50s, and maybe in control theory, where researchers try to model stuff like rockets, for example, right? So how like the state of the rocket and the location, the position of the rocket evolves over time. Back then, it wasn't based on the raw input sensory like images. It was just based on some high-level state. And usually the dynamics model or the forward model, which is called robotics, is really just like, a set of equations just written by hand. And I think this new concept of a world model is usually what we treat, when we say world model today, we talk about models that are based on the input sensory, like let's say image or a video. And usually the model is a deep neural network. So it's not just like a linear model or one that can be just easily written by hand, right? So for example, if I care about the rigid motion of an object, it's something I can write by hand. But if I now want to model, very complex dynamics in the world, like how different people walking across the environment, or if I cook some meal, so or I cut a tomato, right? So the state of the tomato changes when I cut it, right? So I think this is like one of the biggest appeals that we have right now for word models. And so this is maybe just quick introduction of what is a word model. And there's also the question, also there might be some background noise, ambulances going by. But there's also the question of why do we need word models, right? I think it's also an interesting question, but I think one of the ideas is that if we have a good word model, then now what we can do, we can use it as some kind of simulator of the environment, right? We can start, for example, feeding a current state and then start simulating different kinds of actions we can take. And we can look at the outcomes of these actions and see which action leads perhaps to the outcome that we want, and choose the actions that minimize some cost or leads to the kind of outcome that we care about, right? So this is one idea of why word models are useful. There's some other ideas. If we want to build a simulator, then maybe we want to build a complex simulator of the environment dynamics, which is just not just like a simple one that can be just written by hand, like using some physics laws or something. So this is like one idea. Yeah, it's long. Feel free to chime in.
Okay, I don't want to start this off by being a pedant, but you keep saying these are states? Aren't these would be observations though? These aren't full states, right? Okay.
Yeah. So
is that important in any way, or I don't know?
I think it is important in this particular paper. Well, we also treat them as kind of observation, and we encode the images to some kind of latent state, and we operate over the state. Yeah.
The state is actually latent in this. And so by predicting the observation or presumably learning like some underlying state vector representation that's not these images, right? Is that kind of the idea? Or is that
right?
Okay.
I mean, you probably want to learn some encoder at least that can, map the observations into some states. You don't have to keep the full dimensionality of the input observations, but
I was just curious. That makes sense. All right.
Yeah.
Cool.
Yeah. Okay. So I can just jump into the paper, or if you want.
What did you do? So you learned this. Yeah. Sure. Tell us.
Okay.
Tell us more.
So here So here we focused on a very simple, maybe one of the simplest world models that you can think about from the perspective of embodied AI. So you have a neural network. This is what you see here. That is taking a sequence of observations. These observations are just the images from the point of view of an egocentric agent, like a robot. And you're also receiving an action. And the action that the world model receives is how the robot is going to translate, just move, how is it going to rotate. And then there's another parameter, which is the time dynamics. Like how much do you want to forward the time to the future or go backward into the past? So you can say, okay, I want to maybe go forward in like 1 time step, or you can say, I want to go forward in like 10 time steps, okay? And what this model does, and the idea that what this model does is tries to simulate the future by applying this action over this past observation it received and output the next state. In this case, we show the state decoded to, the next observation as well. So there's also a decoder that takes the state and then decodes it back to pixel space. That's what you see here, an example of applying this. One of the ideas is that if you learn a good model like this, now what you can do is that you can take this world model and you can condition it on some first image. This is an example of an image in the UC Berkeley halls, right? And then you can also condition a sequence of actions. This is this arrow that you see here. So it's a sequence of action. It only describes the translations of the agent. And now what you can do, you can roll out this model. Taking the first image and the first action, you input it into this model here. It output the next observation, the next state. And now you can kind of like feed it back autoregressively. Take the next action here and simulate roll out this entire sequence of states. Just by simulating these actions, right? And obviously, this is an environment that the model sees because, as you can see, it can basically reproduce this environment at Berkeley pretty well. And now you can try to use this model to simulate multiple kind of futures or multiple kind of actions, right? On the one hand, you condition on this trajectory here. On the other hand, you condition on this trajectory here. And you see where you ended up with. And if you want to navigate to some object, for example, this blue and the gray beans, now you can measure, okay, how close am I actually to, in the end of these trajectories, to this goal state. So you can kind of like in a goal conditioned way, try to search for a trajectory that minimize some cost. That's the idea. The cost is just going to be the similarity to this input goal image here. Okay, does this make sense?
Yes, Ahmed. So I guess you're saying this is like the world models is trying to predict something that is in environments that is seen in this training data set, right? So what if in this, let's say this Berkeley Hall, what is during the training or in the original data set, there are actually moving objects. Let's say there are people walking around. Also, like if you try to ask a world model to imagine, will the moving object also show up?
So what we see, and just based on some visualization of this model, and I can jump into some examples of this as well, is that the model is able to, so these are examples of simulating different sequences of actions in different environments, which are known. And in some of these environments, there are actually people who are walking. And for example, if you see here in these images here, just on the bottom, on the middle of the screen, you see there's some, so the first image does contain some people which exist in the environment, and we condition the model on this image, and now we ask it to simulate some trajectory. And what the model does, it tries to basically simulate some of the motion of these people in this environment, right? So it's not 100% successful, and I think there's probably still a lot of room to improve in this aspect in learning the dynamics of how people move and in dynamic objects in the environment, which is something that I think would be probably learned with more data. But still, the model does try to simulate this, which I think has definitely a certain appeal, because this is something which is not that easy to simulate with just a simulator and with rules which are just written by hand. Yeah. So yeah, we can also try to apply it on some unknown environments, which is what you see just in the top right here. Right, you just do the same. You take some image from the internet, and now you try to simulate the trajectory, like in here or like in here. And this task, I don't know, I feel like it's a bit less. So the motivation here is not really clear necessarily for navigation, right? Because the model is gonna try to carry some visual prior to learn from other environments to here, and so it could guess maybe how the trajectory will look like. It will result in imagination, but it's not gonna be necessarily something which follows the actual environment. Although there are things which are common between environments, right? So if you want to exit the house, and you're in the second floor, usually you have to take the stairs down, right? So this is something that is kind of general. If you learn this prior, you can try to carry it over to a new environment.
Cool. Yeah, I suppose the holy grail of this is that if this really works for unknown environment, then you can have a continuously unlimited data that looks real, and then just like simulate ton and ton and ton, almost unlimited. Oh, well, I guess limited by your compute of producing like realistic training data. Is that the idea?
Yeah, I think if you have a very large and diverse data set of videos, maybe you can learn priors that could be interesting both for imagine like creativity purposes and for maybe to learn some priors from these environments that carry to new environments. This is the idea. We tried it. I think in terms of the data set that we have, I wouldn't say it was large and diverse enough for us to actually maybe solve this kind of task, which I think it's really hard to this generalization to new environment. I think it's not that easy, and I think it's something that I think we should probably, and we are currently continue working on.
You think there are cases, so you do think that like this would scale if you had a lot more data, like 1,000 times or 1,000,000 times as much data, then you could get it to work in new environments?
Yes, I'm pretty sure. Yes, I'm pretty sure.
Okay.
I mean, I don't mean that it will be able to necessarily navigate in or simulate trajectories in unknown environment in a way which is faithful to the real environment, right? Because it hasn't seen it, so there's obviously uncertainty. Right? But it will be able to make completions which make sense, or or generate a sequence that kind of like follows something which makes sense.
Yeah, that makes sense. So if you were generating alternate so then you could use it like Michael was saying to generate like lots of data in that regime, or you could, I guess, condition it maybe on the environment and then it can figure it out somehow.
Yes, or if you have a very long context window, like let's say a minute of frames that you can stack in your context window here, then maybe that's enough to actually, and maybe you can feed in the crucial aspect of the environment, and then maybe you can just do it. You don't really need to retrain or anything. But this is not the case here. Here we only have in this paper we only have around 4 frames of context, and so the context size is actually pretty small, and it's actually very limiting.
Yeah. It would be pretty cool if given like a sparse set of observations of an environment, you could like get a full functioning generative video model like this to work, right? Like something so you could actually make it like, so you could plan somewhere that you hadn't like fully explored, I guess, or trained on. But yeah, that's very cool.
Right. So what we have like around this, so we have some examples of how do you apply this model on environments which were seen first. Now, you can see some of the visualizations, so they're not great, right? So you look at this airplane, you take a right turn, right? And this airplane here, it's kind of like distorted. Or you look here and the castle. So if you look at if you're nitpicky about the details and you see something here break. So, but the idea is not to say we solved out distribution generalization or generation. The idea is to say that you can actually take multiple environments, one which are outdoor, one which is indoor, one which is another outdoor or something. Distill them all into a big diffusion models, and it actually learned priors which can carry over into some new unseen environment. So I think this is kind of like show a bit of it, right? And there's definitely need to be more research progress to continue this line of work, though.
Where did you get the data from for all this? Like, where did you train on?
So, I mean, actually, we trained on
synthesizing. Okay.
So we actually trained on these data sets, which are, I think, very common on for visual navigation. So data sets which were, so a few data sets, one is a Recon, another one is a Tartan Drive. There's another set called Euron for social navigation in the Berkeley halls. So I think it's around 200 hours of data of different robots. So another, I think, interesting part here is that we train a single model, a single world model across different environments and embodiments. So you can have iRobots in the data, you can have cars, you have these iRobots and others. So I think in terms of world modeling, this is actually something which is not very common, especially, by the way, in model-based reinforcement learning, where usually a world model is coupled with a single task, a single agent, and a single environment. And the goal there is to basically reduce the amount of interaction or the number of interactions that the agent perform with the environment for learning. And here we kind of like relieve ourselves from some of these assumptions, and we just say, let's just train on diverse set of agents, diverse environments, which I think is pretty neat.
Yeah.
And sorry, in those data set, you have like the video and also the actions, right? Is it?
Yes.
Of
so we
those
have the
robots.
video,
Okay.
and we have the trajectory of the agent, which is basically a sequence of the camera poses of the agent across time. And some of them, I think, are obtained via GPS, some of them by IMU, and using like, I don't know, some of them just apply some wheel odometry to wheeled robots to actually get the signal. So it's a, but yeah, maybe we go into a few of the assumptions here. So in terms of the formulation, so I mean, the main idea is, like, as I said before, I want to build a generative model, one which is hopefully stochastic as well, because the environment is stochastic. So maybe if we can build a world model which is stochastic, it's going to be beneficial as well to see some dynamics which change, and maybe can also be useful for maybe training agents later on. And a world model denoted by F, it's going to take a state and an action. The action is just going to be right. So how the agent translates and rotates the environment, and the time shift, which I mentioned earlier. And then given the past state, which includes, there's a lot going on, which includes the past sequence of frames, this model is going to we're just going to be able to sample the next state from this model. And the state is, how is the state defined? Is we take an observation, we can encode it via some encoder. Here we use a VAE encoder, the one which is used in stable diffusion as well. So we take a frame, we encode it using the stable diffusion VAE. It's a continuous encoder, and this is our encoding. And the idea is that it just reduces some of the dimensionality of the observation, so it's easier to train on this and work on it. There's another part which I think is quite, we find quite important. To actually train this model, we don't just predict the next frame in the sequence. What we actually do is that we choose, there's a hyperparameter, not a hyperparameter, a parameter called K here, which is the frame we're actually predicting. So let's say it with a time step T. What we're going to do is that we're going to choose some random time step. This time step can be up to, let's say, 16 seconds into the future, or 16 seconds even into the past. And we're going to randomly choose it. And now what we're going to do, we're going to say, okay, the next state we're going to predict, or the next state we're going to predict is going to be this shifted state, right? Why do we want to make predictions which are not just the next state and can also vary across time? The reason is that we found out that if we just make prediction to the next state, the model just completely ignores the action. It can just resort to, let's say, let's memorize the data, memorize what's going to be the next frame, ignore the action, and we always kind of like can guess, right? If I'm kind of like looking right in this direction right now, you can make a very good guess where I'm going to go, and I'm probably going to take a step towards this direction, right? I usually don't really rotate that much or something. So the model can just ignore the action, right? And that's the point where that we actually try to, instead of just making prediction one step in the future, we kind of like challenge the model and saying, okay, we're going to tell you, instead of making a prediction to the next state, we're going to just sample some random future state, and we're going to try to approximate what is going to be the action that leads from the current position to this next state. And this approximation is just going to be, we can just sum all the translations, all the changes in translation, right? If I sum all the changes in translation from this point until this future time, this future plus k time step I'm going to arrive to, that's going to be my new action. And in terms of rotation, we're going to sum as well, but we're going to take it like modulo, so we don't go beyond 360 degrees, basically, or 2 pi radians. So that's the idea. I think it's a very simple idea. Now, of course, it's approximation, right? So let's say that let's say I'm here, and there's a wall in front of me, but I kind of like circle around the wall, and then I sample this time step, which is around the wall. So what's going to happen is that my action will just tell me go through the wall, like it's just going to be a straight line through the wall, and I'm going to immediately end up here. So this is what I'm saying, it's approximation. So you don't really walk this way through walls. So you kind of like teach the model to break some laws of physics in some sense with this approximation, but it kind of like solve this problem of the model just ignoring the actions. That's
really interesting. That's a really useful observation, actually. Like, nice to hear. I guess you could like send in trajectories of actions or something instead. I guess that's also very difficult. I don't know.
Right.
Yeah. That's cool.
Yes, I mean, you can think of it, if you have enough data, you have some counterfactual which are natural in the data already, right? So let's say I'm moving in space, and now I'm arriving at some point, and this time I'm taking this action towards there. It's possible that if I continue walking, I'm going to end up in the exact same location, but next time I'm going to take the action there, right? So I'm going to be conditioned on the same context, but one time I'm going to take this action, one time I'm going to take that action, and that's the only thing that's going to distinguish these two actions. So if you have enough data, and if your data is diverse enough, maybe you can get around without this hack, because this is some kind of, I see it as some kind of hack because we break some physics here, but it's useful. It's useful for the training, and we found that it leads to better controllability of the model.
But I do have to wonder, like, if it can teleport through walls and stuff like that, is that going to hurt the planning performance? I guess you're saying it doesn't really end up mattering. So that's good to, like, if I wanted to use it as a navigation planner, like, I can't.
I mean, the reason I'm upset that it hurts the physics, because I actually want to learn world models which are faithful to the physics. So if you go through a wall, I want the model to learn that the wall bounce you back, right? So I don't want to teach a model that you can actually go through walls. In practice, what we see is that since you never actually take one step through a wall. If you walk through a wall, you actually just let's say walk through the next room, right? So kind of like circle around, you go to the next room, and then you'll step. So what we see that usually what happens if you try to walk through walls, something will break a bit, and then it will not hurt planning because it will just lead to a bad trajectory anyway. But still, I think, in some sense, the fact that we're using trajectories from robots that were obtained through visual odometry or IMU are already not super some approximation, right? Because let's say it's possible that your iRobot bounces through a wall, right? You don't get the action that tells the iRobot go through the wall. You don't observe this. What you observe is just the result of this action, right? Because if you use an approach like SLAM or visual odometry to stationary for motion, if you use some of these approaches to reconstruct the trajectory of the agent, you only get the trajectory which is observed. You don't get intended, kind of like latent trajectory the agent tried to take, right? So it's already some kind of approximation of the actions. But yes, so okay, I think it's an interesting discussion. I don't want to take too much of a tangent, but okay. So this is how we basically construct the actions and choose the state and actions and the prediction targets in this model. And another question is how do we actually train this model? What is the architecture, et cetera, et cetera. So the main idea in this architecture is to use diffusion transformers. So diffusion transformer is just a very standard transformer that is adapted to use to be used in diffusion models. So diffusion is a generative model. Yeah, how much do I need to get into all these details? Diffusion model is a generative model that basically has the training objective of we apply some noise over the input, some random noise according to some schedule. Can randomly choose to completely mask the input essentially, or we can randomly choose to just apply a bit of noise. And then the goal of the neural network is to denoise, essentially denoise this input. And here we care about the conditional case. So you can think about it that we have some context. The context is, let's say, some past frames. They are completely observables or not masked at all. And now we have some target we're trying to predict, some target frame we're trying to predict. We apply some noise on top of it, and we try to denoise it. And the variant that we use, we call it the conditional diffusion transformer. And so it's a standard diffusion transformer that also has some conditioning over the past frames. And so the conditioning is done via an adaptive layer norm layer. So an adaptive layer norm is basically a layer that modulates the normalization of the input in a transformer. So when you apply the layer norm normalization, which is part of every small component in transformer, both in the attention and both in the feed forward, if you adapt this normalization, you can get pretty strong conditioning behavior. And the way we form this transformer is that we start with attention, right? Just like any transformer. The attention is happening in the current frame. Tokens from the frame we're trying to denoise can look at each other, right? So if I'm going this direction and the image I'm trying to reproduce, tokens in the image I'm trying to produce can kind of like look and interact with each other on the first attention layer. And then we kind of like enrich this representation of the layers that of the output we're trying to denoise with some of the past observation through a cross attention layer, which basically says, okay, I mean, you want to denoise these current tokens. Let's kind of like take a peek in the past. Let's see what was the past. And maybe we can get some information there. We enrich this information. We kind of like add it back. And here we have a skip connection to the denoised part. And that's followed by a fully corrected layer as well. Or fully corrected just an MLP, feed forward small neural network. And this block kind of like repeats multiple times. Okay, so this is the basic architecture. Yeah, this is the basic component.
Yeah, Emil. So I saw some in the paper that you highlighted that this, I think it says here that the blocks of complexity is linear with the number of frames.
Yes.
I think that's one of the kind of the contribution, right? Could you like elaborate a little bit on that?
Yeah. So usually when you have a standard transformer that let's say you want to diffuse, so you want to generate a video over of k-frames. So you have k-frames in the input. And now when you apply a transformer, every token in the input, every token within this within these frames can be a query that interact with the other queries as keys and values. And in this case, the only queries that we consider on the attention operation here are queries from the image we're currently denoising. So if you look at the current queries and the attention that we're performing, then every query on the current image, so let's say that every image has n tokens. And let's say you have m frames in the context. So every token out of the queries that you have n like this can look at any tokens from the past. So you have m times n like this. So the complexity is, let's say, m n squared times d, which is, let's say, the dot product between each query and value. Now, if you have a transformer that looks at the entire context, then now you have, instead of having just n kind of tokens in the last frame you're generating, you have m times n tokens queries that are all across this image. So the complexity is much higher, basically. So you get n squared term in the attention complexity. That's the idea. I hope it makes sense, because you just have, m times n queries instead of n queries. So that's the difference.
Yeah, but But what is the trade-off here? I mean, you remove the complexity, but what do you give up?
Good point. So the trade-off here is that when you generate the current frame, so the tokens from the past are not evolving through the transformer. That's going to be a trade-off. So usually, let's say, if you let's say that you're using just a diffusion transformer instead of this architecture to produce every frame at every time step. So what's going to happen is that every time you apply the forward pass, so each one of these tokens is going to actually, the interactions between them is going to change because you introduced some new frame that you're generating right now and change the past context, right? So that's what's going to happen. And it's going to, and this computation is going to evolve layer by layer. And here it's not the case. You reduce some of the complexity of the forward pass, essentially.
Do you lose anything by doing that? Or do you think this is basically, it works out better this way?
We actually say that it works much better in this way.
Right. Okay.
Yeah, so actually, so we have this here where we just try to apply, diffusion transformer at every time step. And what we compare here is the floating point operations. This is the x-axis. So less floating operations is better, right? Because it means you can use less amount of resources, right? So this is lower is better here. And LPIPS is just going to be the perceptual similarity of your prediction compared to the ground truth. So let's say what I'm going to do, I'm just going to take in a past sequence of states and action. I'm going to make one prediction into the future. And I'm just going to say, okay, how accurate is my prediction using a perceptual similarity metric? Perceptual similarity metric is just saying, let's feed in this predicted image and the ground truth image to a neural network and check the dot product, for example, between them.
So the lower the better.
Yes, the lower the better. Yeah. So it's not dot product, so it's loss. So I said dot product
higher
now,
similarity.
but
So higher y-axis is better. Lower.
No, lower is better. Lower is better.
Lower for both. Okay.
Yeah. So it's loss. So it's a loss. Loss.
Okay.
It's a perceptual similarity loss. Yeah.
Yes. Yeah. Okay.
Yeah.
Okay. Yeah.
So I mean the bottom line here is that if you just want to generate next frame, for practical reasons, use this conditional diffusion transformer that we propose it. It is possible that maybe in much larger scales, like I don't know, tens of billions of parameters, suddenly we'll see that the diffusion transformer is actually better. But in this scale, which is let's say 1 billion parameters, and we see a clear advantage here. Yes. So this is about the model. There's another point which I think is quite interesting about this model, which is the action embedding. Let's see if I can show it here. So the action embedding. So how do we embed actions? So we take in this, so we take in the translation component and the rotation, and we map each one of them into some, okay, I call it like d divided by 3 dimensional vector, because we have like we have, basically forward, backward, we have left, right, and we have your rotation. This is the space of action we use here. Okay, so we have like 3 scalars. We can embed each one of them into a d-dimensional vector and then concatenate them into a single vector of d-dimension. We also have the diffusion time step, which is just when you train a diffusion model, what we condition the model on what's the level of noise, basically what's the level of noise that we have right now, so it can denoise it correctly. And the last thing is just going to be what's going to be the time skip into the future that we're predicting. So we have 3 different vectors. And the way we use them, we combine them, is just by simple summation. So we map each one of them into this d-dimensional vector, then we just sum them. The reason why I think this idea is useful, because then let's say that now you want to train on a new unlabeled data. Let's say Ego 4D. I don't have the camera poses for Ego 4D. So what I can do now, I can just, instead of summing all these 3, I can just sum these last 2 here and omit this one. So I can potentially train this, both on the label data, the one that has, the full trajectories, together with, some unlabeled data. And we tried this to some extent. And to some extent, it it shows, better results when you train this on Ego 4D as well. Specifically, if you want to apply this on some of the the unknown environment. So I think that's where we see some improvements in terms of picking on, some visual priors.
Yeah.
Okay, makes sense. Why not just add in like extra tokens for actions? Because that just doesn't fit with the architecture, I guess. Doesn't work well. So just overly complicated, I guess.
Extra token for the
So
transformer.
like in the input, in the context.
Yeah.
Why not?
Yeah. So the original diffusion transformer paper tried to, so they didn't do like conditioning on this kind of actions or on actions at all. They tried to do conditioning on class categories, and they found that this kind of adaptive layer norm conditioning is better compared to.
Gotcha. Okay, that makes sense.
So we just followed it. We didn't try to do anything else, but
makes sense.
But you might want to try it if you. So one disadvantage of this, for example, is that we only condition on the last action. But if you want to try to condition on the last,
I see.
Hundreds of actions, then you might need to do something like this.
Because that goes to my other question. Like earlier, I was wondering why you weren't doing action trajectories. Because like this actually explains that as well. Because like the way that if you asked me as a roboticist to implement this, I would imagine you'd be giving it a trajectory and predicting a trajectory, because then it solves a couple of these little issues that you have, like the time stepping and the physics. But this explains it. So it's basically just that image generation is not possible that way. Because am I understanding that right?
I think in terms of like predicting a trajectory, you're saying like predicting a trajectory of images or of actions?
Both. Well, given a trajectory of actions, predict a trajectory of images.
Yeah. I mean, so this model is autoregressive, so you can basically apply it when you train it. You can actually train it in autoregressive fashion. You take a sequence of images and you can just train on each one of them. But yeah.
Right. Yeah. Okay. Yes. But
predicting the actions is just not is not the kind of like part of the problem statement. We're gonna get into how you can actually use this model to plan, which is gonna be how we're gonna come up with a trajectory of actions to achieve some goal.
Yeah. Okay. Yeah. Cool. Sounds good.
Okay.
So how do we use it to plan?
Okay. So another question is like, how do you use this for planning? And the main idea is that let's say that someone give you a trajectory like this. Let's say someone gives you a sequence of states and a sequence of actions. What you can do is you can define a cost function or a loss function that says, does this sequence of state and action achieve or lead to, some target outcome or some S star, which is going to be some target state that you care about. Someone give me a trajectory just like we saw here. Right? Someone give me a trajectory. It has action, it has states. Now I can say, does this trajectory actually lead to my goal? Yes or no? And I can just use some scoring function that measure this. How close is this to the goal, right? And if I want, I can also, apply some constraints. I can say, don't go into the kitchen. We don't actually do this kind of complex constraints, but you can say, okay, don't go into the kitchen because the floor is wet, or there's a cat, or I don't know what. So you can apply also some constraints on this and say, okay, this trajectory, I'm going to discount it because of that reason. It's not it's going through the kitchen, right? But then I can define a loss function or a cost function, and the reason it's useful, this is just basically becomes very similar to a model predictive control problem, and you can try to apply some tools to minimize this cost function with respect to actions. So you can try to say, okay, now that we have this cost function, now you can say, okay, so given this world model that we have, what sequence of actions will lead me to this target goal? And we can search, right? We have this world model. I can take this trajectory, see where it ended up. I can take this trajectory, see where it ended up. But we're not actually doing like completely random search. We're actually using some optimization tools that well, actually the kind of population-based, at least, approaches to minimize this cost function and find a sequence of actions that can lead you to the goal. Okay, so this is the general idea. Does it make sense? It's kind of like answer a previous question, Chris, about like how do you actually use this to plan, or?
Yeah, I think this makes sense.
Well,
yeah.
I guess the goal here is an image goal, right? And this image goal could
Yes.
be maybe like so is an unknown, I guess, like time steps ahead, let's say. And so, but you're just asking the world models, okay, given some arbitrary like trajectory and like
Yes.
like
So let's see
would I
some example of this.
yeah.
So you have some input image and you have a goal. So this is the input image, this is the goal.
Yep.
Right? And what you see here in blue is a trajectory, the ground truth trajectory from going from this input image to the goal, right? Just kind of like go right and left. Then you're gonna face this goal. And now what you can do, let's say someone gives you let's say some oracle gives you, okay, take this, number of trajectories. One is this red one. The other one is this green one. And now you have to decide, and there's going to be another one, the yellow one. Now you have to decide which one is the best. So what you can do, you can take the input image and this sequence, how do I freeze this? So you can take this sequence of this input image and this P1, P2, P3 and stimulate each one of them using the word model. And now you can compare which one of them matches the goal the best. And just measure some perceptual similarity between the goal and just the one that leads to the best outcome. So the problem becomes a search problem. So it's not like the usual thing that we usually do in deep learning, right? Usually we just have a neural network that, with a policy, right? So it takes, let's say, an image, let's say a navigation policy, right? So it takes an image, and what it does is try to predict, let's say, an action or a sequence of actions to achieve, to minimize some,
How do you tell whether or not, how do you generate those initial candidates, I guess? Is that random sampling, cross entropy?
So this is a good question. So what I said earlier here is just using the cross entropy. So here we didn't make any assumption about the action space, just use the cross entropy method. Another thing you can do if you have access to some generative policy, right?
Cross entropy method relies on an initial estimate though, because it's an optimist. So where does the initial one come from?
So we define.
Oh, sorry. Oh, you define. Okay, yeah, makes sense.
Yeah, so we define some prior over. Right. Yeah. So the way cross entropy works is that you define some prior over, let's say, the actions, for example, and now what you do, you're gonna sample a few trajectories, right? And you're gonna see, okay, which one actually performs the best, and now you're gonna, based on this, take this top K best trajectories, update your prior, and do the same process again. Sample multiple trajectories. Stimulate them using the word model. Look at the ones which perform the best. Update your priors, until you converge, hopefully.
Yeah.
Yeah.
Cool.
Yeah. So this is like one idea.
Yeah.
Go ahead.
Yeah, I mean, I guess you could also train like a policy or something that would hopefully give you something. Yeah.
Right. So the visualization that you have here is basically using a model which is called Nomad. So it's a paper that was, I think it was chosen as the best paper in ICRA last year. It's from a group from UC Berkeley.
So Michael's dropped off. Yeah. Anyway, cool stuff. All right. Yeah. Continue. Well, I guess we'll. Yeah. Have you tried? Did you try? So this is Nomad. So you're on Nomad. So Nomad is could you tell me a little bit about how you use that? Oh, that's a baseline. Gotcha. Okay.
So you can kind of like work this jointly. Right? You can say, okay, Nomad is going to generate your trajectories. Like here, for example, Nomad is the method that generates your trajectories. And now you can say, okay, instead of just relying on just like sampling trajectory from Nomad, instead just, sample 5 or, 32 or 16, evaluate them, and choose the best one using the word model. And this is something that we've done. And we're showing in the paper that this improved the performance over navigation with Nomad alone.
Makes sense. Cool. Okay. Yeah. So great. You can, so Nomad gives you the trajectories, you can improve on them. Great. Cool.
Yes.
And yeah, because that was the other thing, because like that image similarity loss like really relies on you getting very close to the actual goal for it to be useful for like cross entropy optimization. So like then you do need some much stronger signal, I guess, if it's a hard navigation problem. But like using something like Nomad helps solve that. Okay.
Yes.
Yeah.
This would help. And we found that like if you just want to do a planning of navigation for just 2 or 4 seconds into the future, we found that you actually don't need this signal. So if we look, I think we have some
Because you can just generate like a lot of samples, and that you can saturate, like you can generate enough samples in that space that you will likely get something valuable. Is that kind of the idea? Or yeah, no.
Yeah.
Okay. Yeah. No, that's real.
So
That makes sense. Yeah.
so it's a bit of perfect just
Yeah.
like hours, but I think it does at least show that this image-based is
Yeah.
right. If you don't, if you know, you navigate that far to an area and you don't see in the image at all, you don't get any signal, you know, from the current image observation you have, it's going to be hard to, like you're saying, using a approach like cross entropy method to just long-term planning.
Cool.
I think, by the way, this is in general a big problem right now in world modeling. Like, how do you plan with, you know, a large neural network which is differentiable?
Yeah, I mean, I feel like with any good with like robot planning, you always want to be able to throw samples very far out into the future. Like I actually think like something like the time offset would take larger steps or something, but it's a really interesting problem, definitely.
Yeah, and by the way, this is something that we can do in the planning as well. So we can say, okay, so instead of like just planning one frame ahead, you can say, okay, let's just like take one big steps and explore hierarchically, you know, like first go very far and then you'll see where the goal is on some radius, right, or something. We haven't done it here, but you can
actually think that's really cool because like you have the 16-second step. So if you can only plan a few steps out, but you can take the 16-second steps and then find a plan using those large steps and then plan to each of the intermediate ones and so on. And you could generate probably a pretty good planning algorithm there, right? Something like that. Yeah.
Yes, you can potentially try. We haven't really tried you know, this kind of idea for planning, but we did try to evaluate at least the quality of the simulated trajectories over time when you try to roll out, let's say, up to 16 seconds into the future, either in jumps of like, let's say, just, you know, one time step, or if we work on 1 frame per second, which means like basically jumping 4 time steps in each jump. And we basically see that they don't perform. I mean, if you take actually one step, like what you see here is like on this right plot here is let's try to see if I can zoom a bit into it. But what you see here is like the horizon. When you roll out you start from one example. Now you're gonna roll out the world model based on some given actions, and the world model is gonna kind of like make a prediction, then, you know, feedback the prediction, take the next action, and simulate this entire trajectory. So what we see here is that this blue line is basically simulating a trajectory at 1 FPS.
Okay.
Right, and this one is at 4 FPS. So on the green one, we basically generate more frames. On the one hand, you make small, kind of like incremental steps, but you have the chance to make an error in each one of them. Whereas in the blue line, you make larger jumps, like you proposed before. And then you might offshoot big in each one of them, but then maybe you generate less steps, so maybe it's actually the chance of making a mistake is also smaller. So we see they're kind of like comparable. You know, jumping on 1 FPS, like big jumps is slightly better.
Well, I'm wondering if you could like. So there's this thing in like with a lot of robotic planning, right? Where I want to plan, where I have an intermediate goal. I generate I can sample an intermediate goal that I want to try to plan to, or something like this. Like particularly for complex robot planning problems. So so one thing I can imagine doing, like if you really want to solve for a hard goal that I don't have a good image, like that I can't, like I could generate. Maybe I generate a bunch of these 16-second jumps, and then I try to plan to one of my generated jumps to see if I can like actually generate a course plan. Would that kind of thing work? Is that like, can you plan to does that make sense? I don't know.
You can try. We haven't tried this. We haven't do like the sub goals. Another thing which is done in reinforcement learning is that you have some reward model. So you can say, okay, let's roll out my reward model, let's say like case steps into the future, and then from there we're gonna score the state we arrived to using some reward model that tells me, okay, this one is better than this one. Then basically you hope the reward model is accurate.
Because I feel like these things are really fascinating when they get to the point where they work over really long horizons, because like over just a couple frames, right, I could train a policy, I guess. Like it's, and I would expect it, like, but like once you're getting to like really distant goals, like that, it becomes much less obvious how I do that. That's actually one of the cases where a lot of like reinforcement learning, as you know, like doesn't tend to work as well at really long horizon problems, right? So like that's actually kind of, that becomes really valuable, I think. Or I mean, not that it isn't already, but yeah. Cool. So what's next? What are you going to do next?
I mean, I feel like this entire space of world models is, I mean, like you're saying now, I feel like this kind of application is a bit trivial, right? Like you would think that, okay, navigating by the AI with a world model would be something that already work by now, by 2025. So, but I think there's a lot of opportunities in this space, right? So there's like, how do you build the models? How do you learn without actions? Let's say you have some unlabeled videos on YouTube. Can you actually use them to learn a word model without actions? And there's been a lot of recent body of work on, many researchers trying to tackle these kind of questions as well. But then how do you plan? Like, let's say you have a good word model. Like, how do you use it to plan in a way which is efficient? And so this is also a big area of research. I think there's a lot of research opportunities in this area right now, which are interesting.
Yeah, definitely. Like it does seem like there's a lot of there's definitely tons of unsolved problems in world models. It feels like one of those things that people like haven't quite cracked yet to me, because like, I don't know. Yeah, but it's there's so much exciting stuff happening, right? Yeah. So cool. Yeah, makes sense. So which particular thing are you gonna work on next, or do you think is the most exciting?
Manipulation tasks.
Okay, manipulation tasks. So like that's where okay, cool. That's actually one where I feel like the utility is also super strong, because like the physics modeling for simulation and for planning is so difficult that learning world models there makes a lot of sense. Yeah, too. Yeah, cool.
Right. I feel like also we don't have a lot of data. So world models give you the opportunity to, to simulate many different trajectories and hopefully move some of the heavy lifting from the training data to test time optimization. So you can say, okay, treat the search problem as test time. This test time is essentially this optimization cost problem minimization problem we talked about here, but it's relevant to every world model usually, is interesting because now you can basically minimize this cost function by searching for the best solution. This could reduce some of the need for training data. So I think this is particularly interesting. Yeah. So I think humans and manipulation, I think, is going to be interesting.
Great. Cool. All right.
Okay, great.
Well, so a couple last questions. So one thing that we always ask is, what I guess is like, are there any cool papers that you saw recently? Anything you'd like to give a shout out to?
Yeah, there's this new paper which is very interesting from UC Berkeley just last week about oh my god, I need to find the name of the paper, but I think it's a paper from a researcher, a PhD student named Arthur, and from
Arthur Alshar, is that right?
And,
okay.
Yeah.
Okay. Video mimic, right? Yeah, that's okay. I know what you're talking about. Yeah, cool.
Yeah.
All
right. Basically, it's really reconstruct humans in videos, do some retargeting for humanoids, and then use this as a supervisory signal to train humanoid policies.
Do you think you could use that as a world model training method? Yeah, hopefully, maybe turn that into cool. Yeah. Well, that's sorry Michael had to leave. It was great having you on. It's very interesting stuff. Is there any last things, if there's one takeaway that everyone should get from your paper, what is it? Let's say that. That's the most important thing.
World models are going to be a big thing. They're going to allow us to simulate complex environments, which are not possible right now, both for simulation purposes for different applications, but also for I can see a future where world models will replace RL or more complex training time learning, but just applying model predictive control at test time.
Well, this is like the test time compute thing, right? Like this is the
test time compute thing.
Yeah.
But this is a better test time compute thing, because when you use language models with test time compute, you don't usually condition on actions, right? So you do some chain of thoughts, you generate some trajectories, and you hope to be able to score them and pick the best one. Here you're conditioning on actions. So this is action conditioned. So you can try to look for the sequence of actions that lead to the best outcome. So it's slightly different formulation, which I think makes much more sense for test time compute as well. So I think it's going to be potentially a big thing.
Yeah, it's exciting stuff. It's a cool, it's cool work, and good to meet you again, perhaps, or all right.
Okay, great. Thanks for having me.
Have a good night. Yeah,
Bye.
Thank you.
Good night.
Bye.